Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending today's presentation on how to optimize inkjet printing adhesion for wire and cable marking. Please note that this webinar is being recorded, and you will be able to access both the recording and presentation slides once they're available online, usually within 24 hours. If you have any questions during the presentation, please use the GoToWebinar question tool. You may submit a question at any time during the webinar, and we'll reserve time at the end of the presentation to answer as many questions as we can. Today's presentation, we will cover the following topics: benefits of continuous inkjet printing, how plasma and flame treatment enable adhesion, keys to substrate and ink interfacial adhesion, why ink formulation matters, benefits of UV LED ink curing technology, and again, time at the end for your questions. Using inkjet printing for wire and cable marking has been a game changer for many companies. Benefits include being able to print variable data, the simplicity of a non-contact print process, line speeds up to 1,800 feet per minute, the flexibility of being able to move printing from line to line, and the ease of use of the technology through touchscreens with software to streamline operations based on each of your applications, and of course, cost efficiency. Today we have an expert panel with technology synergies and experience in implementing inkjet printing solutions for wire and cable. With their guidance, you'll be able to optimize technology for your specific operations. With that, let's meet our presenters. Wilson Lee is Enercon's Business Development Director. Wilson has extensive experience in surface treating applications over a wide variety of industries. He has a passion for solving customer application challenges by employing plasma and flame technology solutions. Wilson earned an electrical engineering degree and an MBA from Clemson University. Huck Hyde is a technical engineer and has been with Gem Gravure for over 17 years. Gem Gravure is a family-owned business that began in 1952 and today has 4 locations and nearly 100 employees. With over 35 years of experience with all types of printing, Huck is part of GEM's Research and Development Center in Missouri. His contributions include the development of specialty inks and applications for marking wire and cable. Mike Kay has been with Omnicure for over 20 years, holding positions as Product Manager, Business Development Manager, Senior Market Development Manager, and currently Director of Product Management. He has extensive experience working closely with customers to develop UV curing solutions for medical, electronic, and optoelectronics manufacturing. He's written a number of articles, given industry talks and seminars on how to develop a repeatable UV curing process. He holds a Bachelor of Science from McMaster University in Hamilton, Ontario. With that, I'll turn it over to Wilson, who will get us started by talking about surface challenges.
Okay, thank you, Mark. We're going to talk about, obviously, the prep of the surface, the print, and the cure. So let's get started with some issues that you're going to have with the material. First, about Enercon, I forgot about this slide. I apologize. We were established 50 years ago. We have Corona, plasma, flame, and ozone surface treating solutions. We also have induction cap sealers. This is actually our new facility in Germantown, Wisconsin. And we also do all of our lab trials in Wisconsin as well as at the customer site. So if you need anything, we can do that, again, at our facility or at your facility. We're willing to do either. So that's a little bit about Enercon. So let's get going. All right, so the surface. To print on or to bond to any surface, you're going to have certain surface challenges. The first of which is low surface energy. The materials that you're generally using in wire and cable applications all start with a relatively low surface energy in the 30 to 35 dyne range. There also could be surface contamination on it. There might be some additives in that material that will migrate to the surface that will cause issues with the bonding. All of these things lead to limited bonding sites and makes the surface very hydrophobic. In this case, the ink will wet up and you will not be able to stick to the material. So what does plasma do to help with this? Well, it does 3 things. The first is it helps clean the surface. It can remove organics from the surface and some inorganic impurities. The organics come off as CO2 and water vapor. and it will do a minimal amount with the inorganic materials. Sometimes we have to look at the dwell time, maybe go a little bit slower or add more plasma to the situation to get the inorganics off the surface, but we can do that as well. There is some micro etching involved. Now, this is on the nanometer scale, so you can't see it with the naked eye, but it is adding about 20 to 30% more surface area. And so, as with sanding or ablation or something along those lines, the more surface area you have for something to stick to, the better your bond's going to be. The most important thing that plasma does is functionalize the surface. Sometimes they call this activation. And what we're actually doing is adding molecular layers to the outermost molecular layers of the surface. These are polar groups, generally oxygen groups, hydrogen groups, OH groups, and this is going to increase the overall surface energy of the material. And the higher the surface energy in most applications, especially in wire and cable applications, the better your print is going to be. So what are the basics of adhesions? There are basically two forces that are involved in adhesion when you're talking about having one surface stick to another. Now, that's the forces of cohesive and adhesive forces. The cohesive forces are the molecules that are holding, in this case, the ink together. You can see that in the red there. So the different molecules are certainly attached to one another, and that is a certain force holding that together. The adhesive forces are the forces between those molecules and the surface itself. So on the right-hand side there, you'll see the treated surface. What happens after you increase the surface energy, that adhesive force is higher than the cohesive force. So the ink will spread out and show you the treated surface there. When you do not treat a surface, or if you do something like rain-etch your windshield, what you're doing is creating a very low adhesive force and a very high cohesive force. So then the water droplets on your windshield or the ink droplets when you're printing are going to bead up, and you're not going to get a very good adhesion to the surface, and it's going to be able to wipe right off. So after plasma, in any of its forms that we'll talk about in a minute, we'll hopefully taking that low energy and turning it into a high energy surface. We can eliminate the contamination because that will also affect your ability to print on the surface. We can get rid of some of those additives off the surface levels, and that all increases the bonding sites. And now we've gone from a hydrophobic surface to a very hydrophilic surface. The print will spread out a little bit more. You won't be able to see that, but it'll spread on the surface more. It'll stick better, and you will not be able to remove it very easily. So this is what surface wettability looks like before and after treatment. So before treatment, you'll see that it's a very, again, hydrophobic surface. So you have a high contact angle and a very low dyeing level on that surface. And so what that makes is the ink have more limited bonding spots. Again, we also increase that surface area. So you can tell that on the left side that we've got a smaller footprint that we're actually touching the surface. On the right side, we've got a much wider footprint. Also, you don't have the ink sitting on the top. You have it wetted out all the way across. So again, after the treatment, you have a very high surface energy. The ink wets out, and you're getting maximum surface interface. And again, this is what happens with any material after you plasma treat it. All right, common materials that we treat: polyethylene, PE, PVC, polypropylene, and a lot of different polyethylenes, I should say, cross-linked, high density, low density, EDPM, silicone. There's all sorts of materials that are used. And then we look at the line speed and other aspects of the application. You can see in that picture there, we have two different plasma heads. This is a higher speed application. And the good thing about plasma is it's pretty linear. So if we're able to do it, say, at 100 feet a minute with one head or 200 feet a minute with one head, you can usually double that with two heads or triple it with three heads. So if you have a very high speed application, the number of nozzles will help you achieve what you're looking for as far as energy levels to get a good print adhesion. Here's a table of some of the materials that we treat and where they start in dyeing and where they end in dyeing. As you know, the dyeing scale goes up to about 72, which is considered water wet. So you can tell that a lot of these materials start at a very low dyeing in the 30s or even the 20s. Cross-linked polyethylene with the plasma usually starts in the low 30s, and you can treat it up to a 45, 46. With the flame treater, you can even go better. You can get 60 dyeing with that. With atmospheric plasma, or atmospheric gas plasma, I should say, we can take Teflon up to about 40. That's using what we call a plasma 3 system that we'll talk about in a minute. And then some other things there. You'll see the PTFE, which is also the Teflon, the HDPE. Again, you can show that we can look at the application, we can look at the material and decide what is better, what system that we have is going to increase that dyeing to the level that will get you the optimal print solution. All right, so let's look at the different types of plasma treatments that we offer at Enercon. The top right is what we call a blown arc, and many times in a wire and cable application, it will be parallel to the wire and cable that you're treating, so it'll stay in there. It'll stay in the plasma a longer period of time. That head's about 3.5 inches wide. You put 2 heads in the application, you'll be at 7 inches wide, which will greatly increase your treat speed. Below that, you have the blown ion, which is what most people think of when they think of plasma. The treat width of that is about 1/2 inch, which for most printing on wire and cable applications, that is plenty. And again, you can go a little bit faster with the blown ion than you can with the blown arc. But both are used in this application all the time. They both will increase the surface energy. And occasionally, you'll see that one has a slightly better performance on a particular material. And then, of course, we can use that. And as I said before, we just, if we have to have multiple heads to get it higher and higher speeds, that is something we can do as well. This is the blown ion 500, and I'm probably not supposed to do that, but I'm going to tease the middle picture, which is actually what's called a 750. That's coming out shortly. This is a wider plasma system, and you can put linear jets on these. They're generally staggered. So if you look at the middle picture there, the blown ion 500, those 6 jets are not in a straight line. They're staggered over about 1/2 inch, 3/4 inch on that head. And that is so when you're treating a 2-inch wide area of another material that you want to bond to, maybe you can get a uniform treatment across that material. We also have a nozzle that is linear. So that is 6 on the middle, that is 6 ports. On the one on the left, that is actually 10 ports. They're all 500 watts apiece. So, which is the same level as the blown ion 125, which we saw on the last slide. So that is 6 or 10 times as much power that you're putting on the surface. So again, as I said, it's pretty linear. So if I'm going, say, 200 feet a minute with a single head, with the 10 ports, I can go up to maybe 2,000 feet a minute. With a 6 port, I might be up to 1,200 feet a minute. So these are all things that we have to decide in testing. We will, determine what dyeing level we need, and then in our lab trials or lab trials at your facility, we'll determine how many ports it takes to get you to the level that you need to get a good print. We also use, on occasion, a flame plasma. Now, a flame is ionized gas, just like the other plasmas, but it also has some other components in it. Carboxyl groups, they're generally called. You can go very high speeds with these as well, up to 100, 200, 300 feet a minute. We also can change the burner to a pencil burner, which is what is shown right there in the middle, which is very similar to the plasma. It's going to treat about 1/2 inch to maybe 3/4 inch. And of course, if we need to run parallel with the line, we can have it go into the flame system and stay in there a very long time and get that energy level up as high as we need to get it for your application. So this allows us a lot of flexibility. It is great for in other applications. It's great for our multidimensional surfaces. We don't have that here with the wire and cable, but again, we could turn the flame parallel and pretty much go to any speed that you were able to print to. So again, this is an option. It's not used all the time, but it is an option. Lastly, we have our plasma 3 variable chemistry plasma. That's what VCP stands for. This is used basically for fluoropolymers. So PTFE, FEP, ETFE, PFA, anything that is a fluoropolymer that has that nasty little F in the acronym, those are generally very difficult to treat. The atmospheric plasmas that I mentioned in the last couple slides will not treat those very well. It actually does treat it, but the treatment only lasts a few seconds, so it goes away pretty quickly. And what you have with the barochemistry plasma is you're able to put other gases in there and get a good bond, get a good energy level on the surface, and that works very well with PTFE. As you can see with that wire that's going through the middle, it is also running parallel to the line, to the plasma itself. So that means that we can increase the length of that plasma, so it increases the exposure of the wire to the cable. So if you're running higher speeds, or if you have a particularly difficult material to bond to, we can use a VCP and just increase that width. It's not a standard one length. We can make that basically as wide as you need to. So that's our Plasma 3 for fluoropolymers. Some examples in the field of plasma treating. This is a Nexans application. It is a printing application. That's actually an older version, what's called the Dynamite IT, and that is treating a PTF jacketed wire to enable printing. You can see that Hal Armstrong offered that we were able to meet some of his UL and CSA specs, and we were immediately able to improve the print quality by simply pre-treating the wire before it went into the printing and curing application. So when we far exceed the CSA's recommendations, that of course is a good thing, and we were able to do this. What he says, they were able to do 1.5 cycles without it, and they were able to do 10 cycles after the treatment. So all of these things are very good and will help you with your applications as well. Next, we have this is a little bit different application, but it is just a printing application on a composite or component, electrical component. This is nylon 66. And you can see there from the pictures on the right, we treated a number of these parts, and then we printed on them with and without plasma treatment. And then you do a simple tape test. So you would take the tape, and after the print would look, the one on top would look very much like the one on the bottom until you put the tape on it, and then you do a pull test on that, and most of the ink comes off, and you can see it on the tape itself. If you do that same pull test after plasma treatment, you're going to see that you get a much better bond, and you're not able to rub that off. So obviously it improves your ability to print on something, and you do not want it to rub off, of course. All right, and now this is another application, printing on the bottom of bottles. And this application, on the right bottom side, you can see the plasma coming out through a hole in the line, and then it goes over the printer. So that little slit there is where the print actually is added to the surface. So what you're doing in this application is the bottle's coming by, it's getting pre-treated on the bottom, and then you're putting a date code generally on the bottom of that, so you can obviously track your products and track them once they go to your customers. Again, this is from Best Formulations. This is an application that we do very often, but it's a slightly different application to the wire and cable printing, but it's the same result. So how do we qualify these? Well, first we need to figure out what your experiments are going to be and what your test data is going to look like. So what dyne level do you need? What energy level do you think you need so that you can pass the scratch test or the acid test or the wipe test, whatever those are? Are there military or aviation requirements that are involved? We need to figure out what those test parameters are. Then what we'll do is we'll take materials into our lab. That is a picture of our lab over there on the right, treating with the blown arc. And we can do some testing to see how fast we're going to need to go, or how many heads we're going to need or nozzles we're going to need to get to the energy level that you're looking for. Then we can either bring that into the field with consignment systems, or we can do other things to help you figure out what you need to do. And then we can tell you what dyne level that you're going to need. All of this is designed to make sure that you are easily reaching the dyne level you need in order to print accurately and print consistently, so you don't have any issues. And of course, we want to build a buffer in there. So we might find that you need 45 dyne to get a good print. So we'll obviously create a surface energy application where you're going to get to say 50 dyne or 55 dyne, so that we have some room for error, because there's some other issues with dyne measurements and surface energy measurements we won't get into, but we want to make sure that you've got plenty of room for any changes that might happen in your line. But again, we're going to help you do this in our lab and at your facility. So what else can plasma do? We can assure, as I was mentioning before, that energy level is at the optimum level for your applications. So we do that by creating samples at different energy levels and let you test those. And then we can eliminate and say, okay, we need to be above this number or below this number or in this range to get the perfect application for your system. We can also, it can be used to clean or prep the conductor. This is another application that we do on occasion. So before the jacket goes on the conductor, many times there is oils on that surface or other things on that surface, so that it'll cause the jacket not to stick properly. We're working on an application right now in Alabama. We're doing the exact same thing on a 3-inch strip of copper that is about to be wound and then put into a jacket. And they're going to use a flame treater to treat that. Many times you can use less expensive inks or adhesives in those adhesive applications if you're treating plasma, because you're getting a better product. In a lot of these applications, there are some inks that will right at the edge of sticking or they won't stick. And so plasma gives you peace of mind to make sure that you're not going to have any issues moving forward.
All right, thanks, Wilson. Great information on getting a surface prepared. We're going to shift gears now, and we're going to look at the ink formulations and chemistries. And as you can see here for Andy Setzer at CommScope, the pre-treatment by Enercon and the ink chemistry of our next presenter, Gem Gravure, proved to be key to their success. So with that, I'm going to hand it off to Huck.
Thank you, Mark. I appreciate the introduction. I am Huck Hyde with Gem Gravure. I'm going to talk to you about the continuous inkjet printing that Wilson was talking about earlier, and how the surface, energy and surface preparation is a big game changer, shall we say, for adhesion to the inks of inkjet printing. Gem Gravure, we've been around since '52. Started on the East Coast up near Boston. Joseph Gemelli had decided he needed a solution for identifying wire, as he worked in the wire industry. Went on through and developed inks and machines to actually mark and code the wire like the UL was listening and needing to do. David Gemelli, second generation owner, he brought us into the inkjet, the continuous inkjet in time of the industry. And today we have 4 locations and a little over 100 employees now. And we are the exclusive representative for printing equipment for Koenig & Bauer in US, North America, basically. We use continuous inkjet in a lot of industrial applications. You can see right there on the slide, all through anything, bottling, as food packaging. Wire and cable is our main forte that we concentrate on, because it is such a wide variety industry of different materials that we have to print on, whereas the use of plasma or pre-treatment and the use of Omnicure's UV curing equipment makes it to where we can give you a whole package that meets all your standards and needs for coding and printing. On this next slide, it'll show you why we need the identification. So, a lot of it's to comply with UL and the LLC standards now. You have to identify everything, and traceability as to where, when, and why it was produced, inventory management, gauges, just identify the wire itself, as well as quality control. In-house quality control, making sure that your wire is the best wire you can put out, or any other product you have. It will give you dates and times when that was produced. We also use it as the nice part about the CIJ is the codes that you can put footprints. You can put footage marks on the wire, and no longer have to measure that wire out with a tape measure. You can go by the footprint and the predetermined footage marks put on the wire. The fundamentals of inkjet are such that it uses pressure to drive a fluid ink through a small nozzle, and uses vibration to break that up into small droplets that can be charged and fly through an electromagnetic field and then onto the surface of whatever is moving underneath the printhead in a certain area or trajectory that is predetermined by the charge on the drop. Again, CIJ fundamentals. CIJ meaning continuous inkjet. Inkjet is, people think of inkjet as your home type printers, but this is a continuous inkjet that actually uses a pressure and puts a stream out and breaks it up into drops that could be up to a rate of 120,000 drops per second available to be charged and discharged from the head that printed as a message. They are selectively charged and put into a matrix to show. It's basically, if anybody remembers the old dot matrix printers, that's pretty much what it looks like when the ink is printed out onto the surface. Uses piezo electric crystal to vibrate the drop and create drops out of the stream that's coming out of the nozzle of the inkjet itself. Then they go through a charging tunnel, and the ink is actually, each drop will get a charge and will be deflected through the deflection field into the position it's supposed to be with each passing movement of the substrate under the head. The drops that aren't deflected, this is a recaptured system to where they are brought back into a gutter, recirculated back into the ink supply to be spit out and possibly charged and printed out again. So there's really no waste to this. Only what is going out onto the wire is what ink you are using, or out onto your printed surface is what ink you are using. In the next slide, we'll see that the inkjet, it gives you, this is a working model. So you have your ink at the bottom, sub ink in the bottle. It comes up, it goes through a pump, goes and then off to the left there through a pressure regulator that says, yes, I'm at the right pressure for the right size nozzle, for the right vibration that's going on, through the nozzle and through the ultrasonic vibration to break it up into droplets. You see up at the top where the character signal and charge electrode are. That is where the ink is broken up into droplets, and each drop can be charged, as you can see, going through the deflection voltage, that it will fly out, miss the gutter, and fly into its position to form letters. The next slide will show you a little bit more kind of the way it really works. You'll see the ABC there. This happens very fast. This can happen up to 120,000 drops per second, and we can reach speeds up to 1,500 to 1,800 feet per minute, and print codes is 2 feet long on the wire or on the object moving underneath with good clarity. The ultrasonic transducer is key in this, and it's all in the printhead of the unit. The ultrasonic transducer is what vibrates at the right frequency, and then the ink system is what gives you the correct pressure, pushing out the nozzle to give you what you see here is a breakup of droplets, charging of the droplets there, and then the detection, and then out through the deflection field, like Mark's moving through right now, and out and forms into those letters you see on a sheet of paper or whatever you're printing on. The next slide is basically why we do development of ink development for all these products. We have a research and development center in Nixa, Missouri, which is where I work out of. We have another development center in Houston. The core industry, like I said before, we are with wire and cable is our core industry for us. And that's basically Joseph Gemelli wanted to formulate and make his own fluids for these pigmented fluids, as well as dye-based fluids, which I call fluids. They're inks. We can call them inks to go onto the wire and cable. So he started that, and he has been founder in leading the field in inks and machinery to perform on wire and cable with just about any kind of material you can think of to print on. Inkjet inks, continuous inkjet inks, have to have very, very small particles. The nozzle sizes range from 42 microns to 70 microns on your inkjet printers. That is a very small opening for inks to go through, so we have to make sure that all the particles in those inks are small enough that they will not react together and we'll be able to travel through that system and out the nozzle without impedance. We manufacture and design all of our inks right here in the USA. So when we talk about inks, we have a dye-based ink and we have opaque inks or heavy pigment inks. There's many different terms for opaque. What dye means is it's like food coloring in water. Sugar in hot water, it will dissolve quickly. I like to think of it as food coloring more than sugar in hot water. As food coloring, as soon as your dye hits our solvents, it disperses and never will fall back out. They allow for bright colors, dark black codes. That's the nice thing about the dye-based inks is they'll give you some very, very dark codes. But they can be damaged by heat, solvents, and plasticizers. Even alcohol will take a lot of the dyes and remove them. Just a mild alcohol, isopropyl alcohol. The biggest thing for dye base is packaging and paper. We do have some in the wire and cable industry, but you have to be careful because the dyes will want to migrate or ghost image off onto, if you're printed on a surface and you lay a surface on top of it, it will actually mirror image, or if anybody remembers the old silly putty, put it on your cartoon comics and it pulls all the color off. Same thing. But they do offer very, very ease of printer operation, longer times between maintenances. And as we approach the next part of the slide, we will talk about heavy pigmented inks. They don't solubilize like the dye base will. They are actually particles, okay? We grind them down to small as we can and still get them to stay in the solution. They still will act like, sand in water. It's the best way to put it. They will settle out. Heavy pigmented inks give you, though, the best contrast on dark surfaces because they are pigmented. They hide the color underneath. They won't let like a black wire with a white ink on it, you won't see the black underneath the code. You will just see the white ink on top of it, and it looks very bright. We keep mainly to the whites for the heavy pigmented, but we do have aqua blue, a light blue, and a green, and a very, very bright yellow that we offer in a heavy pigmented as well. Adhesion in high temperature applications is better. With the pigmented, the dyes tend to be a little bit susceptible to high temps. And then, like I said, we have an aqua ink that can be used across most colors of your substrates. Now, we always try to come up with one ink that'll do it for all colors, and then somebody comes up with that color on their wire substrate. So it makes it difficult for us to keep up with the industry when they keep making things difficult for us. Easy printer operation with built-in mechanisms to keep the printers running and keep the ink stirred. It's called a maintenance mode that comes on and stirs every 2 hours and runs the system, keeps the ink moving in the system. And then it has stirs on the bottles on the door of the printer. That's the additive bottles, and it keeps the ink stirred in that way. As we move to the next slide, we're going to see the soft pigmented inks, okay? So what do we mean by heavy pigmented and soft pigmented? Heavy pigmented means they're very, very heavy. Most of the time they're metallic, like TiO2, titanium dioxide. The soft pigmented inks are not metallics. They're more of a pigment that has been colored, basically a resin has been colored. So it takes a little bit more to get them to go into the system and mix into the system. Most of the time we have to use a high-speed shear or even a rotostator type head to mix these to get them ground up well. But once we have them that way, those pigments don't fall out like the heavy pigments. They will stay suspended in the ink bottle and not require the stirring like the heavy pigmented inks will. They still allow for great contrast um, with less pigment, and they can also offer transparent codes like a yellow. You can see a little bit of background color through it. Um, we have more colors to offer than dye-based because of the pigment, but they're still, it's kind of a toss-up between those colors and how they hide compared to a heavy pigment that really, really hides the underneath surface. They have great heat resistance compared to the dye base, of course. And like I said before, no mixing mechanism is required in the printer for good operation of the inks. The ink itself, you've got to have successful your components of your ink or what makes you have a successful inkjet fluid. It's not just throwing some solvent in and throwing something else in and throw this in. It all has to come together to work well in the printer, run well in the printer, and still print and charge well. So we start with a carrier solvent. Okay, this will be a solvent, MEK, acetone, cyclohexanone. We use quite a few different solvents to get what we need to out of these materials that we put in them, which gives us the ink that works for the different substrates. The carrier solvents, they have to support electrical conductivity. Now, MEK will not, so we have to add a carrier with it or another carrier solvent in with MEK sometimes to get it to build conductivity. Most of the time, our resins will be good enough to build that conductivity that we need. The evaporation rate, yes, the MEK, the acetones, that if anybody's ever used them, they evaporate very quickly. So we have to make sure that we keep that evaporation rate in mind as we're making these inks and as they are in the field and running. The machines have a separate bottle of solvent in the machine that will add to as that solvent evaporates out of the ink. Then we come up with colorants. Okay, so we have to have dye, pigments, which they affect the color, opacity, longevity, transfer properties, and general appearance of the print. Okay, what we mean by transfer properties is a dye will transfer, like I said earlier, you have one print, you lay something on top of it, and then you pull that off of it, and you see the reverse print on that thing that you laid on top of your regular printed. That's transfer, and that's mostly dyes will do that. They will, the colored pigments and the soft pigmented and the heavy pigmented will not transfer like that. So then we come to our resin. This is the crucial part of the ink. Not all resins work well with the dyes, work well with the colorants, the soft pigments, the heavy pigments. Some resins will dissolve well, some resins will not stay dissolved. So, it's a very, very fine line you walk with continuous inkjet to try to get the durability and chemical resistance for an ink on the wire or on the application that people would require without having issues in the runnability of the ink in the printer. So resin is a very, very crucial part of this system. And then lastly, but not least, additives. Okay, so we have to have conductivity. These drops are getting charged as they're flying out of that nozzle, and they're flying pretty quickly. You have about 8 milliseconds or microseconds. I'm sorry, 8 microseconds to charge a drop. So that's pretty fast. So we have to have very good conductivity in these. We add salts to increase that conductivity, and it will modify the surface tension. and stabilize the dispersion. Sometimes some salts don't act well with them. It's very particular in the systems you make as to how they are going to behave and how they longevity of the system to run well in the printers. The additives are a big fact in what comes into play with this slide. Okay, thermoplastics and thermosets. Wilson went through and told you about PVC, polyurethanes, and the chlorinated polyethylenes, neoprene, EPRs. There are so many out there that no one ink will work for everything. So, excuse me, we have to rely on our chemist to come up with these inks to work in the printers and based on what their composition is, um, to match the wire jacket composition and have good adhesion. This is where Wilson and the pre-treatment comes in very uh, necessary for a lot of these materials because they have no polar groups, as Wilson talked earlier. They're closed off, and the surface energy is just not there. You have to excite that surface energy to give polar groups for these inks to grab a hold of. The ink characteristic should be matched to the surface energy of the jacket, or the code won't, what we call settle, what Wilson was talking about, how it wets up the actual surface. If the surface is not prepped correctly, you'll see bubbles, little tiny bubbles on the surface. Whereas if you see a surface that has been wetted to a dyne of 42 or 44, that ink will actually go and spread out like it should in a dot matrix instead of crawling up into a small circle. Our next slide will tell us that how we want to go about figuring out what ink we need. So remember the SAFE method. What substrate are you going to be printing on? What material is it? The application. Will Inkjet actually work for this? Or do we need a wheel? Do we need something else, a different type of printing or a different type of application? Finishing, what's required before or after printing? Is there special codes? Is there logos? Is there anything else that has to go with this? And where will this be used? Is there a UL requirement that has to meet certain specifications? What environment it's going to be exposed to? Those are just a few things to ask. You always remember SAFE to get what you need to do. If it's a PE polyethylene, then yes, do a pretreatment by all means. If it's a Teflon or any of those, you're definitely going to have to do pretreatments. Even though we formulate inks for those, nothing will work with them very well unless you oxidize that surface. Okay, so next slide tells us that we have challenges, okay? Major challenges, material properties, mismatches, ink and substrate mismatch. You can get the wrong ink for the wrong substrate. You can use one ink for PVC, but it won't work on your polyethylene. You can use an ink for your polyethylene, but it transfers on your PVC. Many different things you have to take into account, and which is why we readily volunteer to do trials or samples for you and print, and we can pre-treat and post-treat and do whatever, and with the UV cure we can do all that here at Gem and trial your actual composition of your jacket and make sure that you're getting the right ink for that jacket. Contamination is another thing we run into. They get dirty, wires get dirty on the spools, they barrel packed, they get a lot of barrel dust or a lot of dust in the barrels. Some people will even put a anti-caking um, on the wire as it's going into the barrels or onto the spools so it won't tack together. Well, that ends up causing problems for the ink to try to get through to the actual coating, the actual jacket material. It's just trying to print, oil, trying to print on oil. The surface tension then must be changed to where we can get a good contact with the surface, removing the oil where the blown ion plasma is very beneficial. to remove the oil from the surface, print on the surface, and then some of the oils will bloom back over, like Wilson had mentioned first part of his presentation. But once that ink stuck there and the oil blooms back over, then you have a better adhesion because the oil's on top of the ink at that point and you can't rub it as hard. You have not as much friction. We have to withstand, those codes have to withstand very harsh environments. They have to stand up against major gasoline, jet fuels, all kinds of different applications to where the welding cables have to be usually drugged through gravel and concrete and everything else. They want the ink to stand up to all that. Surface treatment and UV LED curing are the best option.
Great. Thank you for those insights, Huck. So we've learned about getting the surface energy and the surface prepared for the ink, the importance of getting the right ink formulation. And now we're going to start looking at now the ink is there, how do we best cure it? And as you can see here, as Jay Ivey of OFS can attest, that adding the OmniCure UV LED technology made the Gem Gravure inks for their application indelible. So with that, I'm going to hand it over to Mike Kay, who's going to talk to us about the keys for successful UV LED curing.
All right, thanks, Mark, and thanks, Wilson and Huck, for the important information, as you said. Getting the surface prepared and make sure you have the right ink and getting it jetted, and now we got to cure it. And if we do that, one of the ways we're going to talk about today is using LED, a fairly new technology that is being used, fairly new to this application, but it's been used for a number of years. And OmniCure, we've been around for going on 40 years now in the UV curing business. Since 2013, we've been part of the advanced lighting division for Excelitas Technologies. And recently, over the last few years, we've added a couple more companies to our UV curing family. We've added the Phosion LED curing as well as Fusion microwave-based UV curing. So we're really now able to offer a full spectrum of UV curing solutions to our customers. When we talk about LED curing between OmniCure and Phosion, we've been working at LED curing systems since the early 2000s, so about 20 years. And over that time, we've worked with hundreds of different customers in different applications, different markets, as they look to transition their curing from what was usually a mercury lamp-based curing now to an LED. And so we understand that there's some challenges in doing that. And that's why it's so important to work together as a team, such as us with Enercon and Gem, to make sure you get a successful application. And one of the things we have that, again, has been really helpful in this is that we have global application centers that can help with this. They can do material testing so that you can see whether or not you have the right LED system for your curing application. And then we have local support that will help run through it right in your process and help you get everything set up properly. And with that, we'll move on to what it is we're going to do for curing. So the basics of curing. So we're going to talk today about the just very basic principles. Within the ink, there's many different components, but when we talk about curing, we're going to look at the photo initiator because that's what really starts the reaction. And when we look at the curing system, we want to look at a couple of things that are really key here, and that's the spectral content of the curing system as well as the irradiance. When you pair the irradiance with the time you have allotted for curing, you get a dose, which is really important to get a full cure. But the sentence I want to really look at is, in order to get the curing process started, you need sufficient light of the correct wavelength range. And that's got to be received by the photo initiator to start the reaction. And that's one of the real keys we're going to focus on when looking at LED. And if you can give it a couple more taps, Mark, I think this one's got a few things to do. But if we look at the spectral content of a lamp system, so somebody who's using a lamp today, they've got that blue chart there that shows you get a very broad spectral output with a UV lamp. And so what that means is you have a lot more flexibility because your spectrum is going to match the photo initiator much more easily. If you look at the LED ones, the green ones, now you're talking a very narrow band of wavelengths. And if we look at the chart to the right, you can see that the uh, the energy
Hang
of
on,
the
Mike.
LED.
We lost the slide there. There we go.
Yeah, perfect. Thanks, Mark. If you look at the energy distribution in a lamp, you have energy all through the UV spectrum, UVV, UVA, B, and C. But on a LED, 99% of that is really focused in one band. And so it's critical that that band matches the photoinitiator and the absorption curve of this photoinitiator. When we started doing LED systems 20 years ago, one of the other concerns was that the LEDs didn't always have enough power to do the curing process. Well, that is really not a problem anymore. A lot of these systems, you're getting upwards of 20, 25 watts per square centimeter of radiance. So there's plenty of power, but the critical is that you match the output of the LED with the requirements of the ink in this case. So why are people looking to move to LED? Well, there's lots of benefits. And the two key ones is you can increase your productivity. But really what most people look at is, if we go to the bottom, they look at, you can really start to reduce your operational costs. So LEDs, you're getting upwards of, depending on the use, 20, 30, 40,000 hours from your LED system, and at a lot less energy. The energy savings for a lot of customers is enough to justify the effort it requires to make the transition from lamp to LED. But there's other things. We talk about higher yields. The LED systems can be much more consistent. The uniformity is able to be controlled, and the degradation over time is much slower than a lamp. So that means your process doesn't change over time, and so you can get a much higher yield. And the other thing it can do is it can expand the capabilities of what you can do. So specifically, if you have heat-sensitive substrates, and Huck talked about some things don't really like that much heat. Well, the LED can provide a much cooler cure than some of the lamp systems. A lot of the lamps, if they're generating IR, infrared energy, it's generating heat. There's none of that with the LED system. So you can have a cooler cure, which means you can expand some of your applications to some things that maybe weren't ideal with a lamp can now be done with an LED. And then if we move on to the next slide, you can see the other one that people are really looking at these days is the environmental benefits of LED. And we're seeing now not only the people producing product, but the customers who are receiving products that are being UV cured are now demanding from their suppliers to be more environmental friendly. And in general, we've always promoted UV curing as an environmental friendly process, because what we're doing on the material side is we're getting rid of the solvents and the volatile organic compounds in solvent-based curing, and moving over to a UV process that now has solids. So the material is more environmentally friendly, and now with LEDs, the actual curing equipment becomes more friendly. So there's no mercury in the lamps, no ozone's being produced, so there's no special venting that's required. The ease of use, there's no shutters. The LEDs are instant on, instant off. So again, it gives you a lot more flexibility in your process. You don't have to be leaving the lamp on as you're not curing. You can turn it on and off instantly as needed. And typically these things are smaller form factor, they're scalable, so they're quite easy to integrate into a process, and that makes it a bit easier when you're trying to transition from a lamp system to an LED, because you can generally fit it into the current footprint, and it makes it a bit easier to make that transition. And if we go on to the next, so when you're looking at a UV curing system, I think the things we try to promote to keep in mind, because as with any equipment, not all equipment is designed the same. And so some of the areas that we really focus on is the actual LED array. For the OmniCure systems, we design our own LED modules. So LEDs are available from multiple different suppliers globally. And we select the supplier, but we design our own modules because we want to make sure that we're designing them specifically for UV curing. Right? LEDs are designed for many different applications, from lighting to all sorts of agricultural applications. And so we want to make sure we take the LEDs and design them specifically for UV curing. Thermals are critical for the lifetime of the LED. If you're not cooling it properly, then you're not going to get the lifetime. And things like the electronics allows you to control the system, and then optics allows you to manipulate the light, because ultimately what's critical is that the light gets down to the substrate for proper curing. So these things are something I'll talk about a little bit more as we go along. To go to the next slide. And I want to talk about what we call the module addressability. So when we look at our systems, a 12-inch system, for example, is made up of 12 individual 1-inch modules. And what this allows you to do is we give the ability to control each module individually. And you can see on the table, depending on the system, it will control the resolution down to about a 1-inch resolution. And what that allows you to do is it allows you to really optimize your uniformity and also customize the light. You can change the length of curing if you want, because you can control each individual 1-inch module. And I'll show you that on the next slide. You can see this is what it would look like on a 12-inch system. You have 12 individual 1-inch modules. If we put the same input power to each of the LED modules, you're going to get quite a bit of variation, because you can imagine there's variation between the LEDs. In this case, each LED or each module has 50 different LEDs in it. And so what happens is you end up with variability in the output, in this case, plus or minus 13%. Not ideal for curing, for a reliable curing. Now, if we move to being able to individually control each module, what you can do is you can measure the output. And this is what we do before all of our systems leave the factory, is we measure the output, and then we adjust the input power to make sure that we're getting much better uniformity across the width of the system. On the next slide, I'm going to talk to you more now about optics. So optics is what controls how the light gets from the curing system to the substrate. And what we can see is the LED light is very divergent. And so small changes in the working distance between the substrate and the equipment can have really high effects on the irradiance. And so one of the ways you can help to minimize that and to allow you to work at different working distances, to add different optics to the system. And so we do that with our systems, and we can really then manage the irradiance much better from what will be seen at the curing surface. And if we go to the next one, this just shows you the different variety of curing systems that we have, different sizes, different wavelengths. We have water-cooled, air-cooled versions. So again, a lot of different options to make sure that you choose the right solution for your curing application. And if we go to the next slide, we'll see when you're trying to select the right UV system, there's a lot of different things to keep in mind. One of the real keys, though, that has been talked about in this presentation, is making sure that the system matches the ink or the adhesive and coating being used. And the LED compatibility is really key here. LED systems are available in a number of different wavelengths. And so it's really critical to choose the correct wavelength to match the application. You need to choose the correct size, obviously, for your application. And then looking at the dose, the irradiance level, often the speed of the application is going to drive that. And there's lots of different ones available. And the other one, though, is the installation consideration. So the equipment is available in either water or air cooled, depending on the environment it's being used in. And some of the environments, can be very dusty environments, or the air can be have some particulate in it, and that may not be ideal for that air to be blowing through the curing system. So in those cases, customers will often choose a water cooled, where it's more of a closed system, and can be a little bit more rugged in a difficult atmosphere. All right. I'll quickly talk about some different fiber applications, as I know we're focusing here bottom left on the wire printer marking, but you can see we're working on a number of different fiber applications. And depending on the application, there's different systems that we would use for the different applications. Top left is riveting. That now is quite a wide cure width, and so we would have a different system for that than we would, for example, for a cable print or for fiber on the right-hand side, where now you're talking a very narrow. And what we're able to do is we're able to use very specific optics that focus the light to get maximum irradiance for the specific working distance that works well with fiber or coloring. So again, depending on the application, depending on the cure width, depending on the speed that you need to go, there's different things that we can do to make sure that the cure system matches specifically with the application. So we'll go on to the next slide, Mark, and there you can see the different applications and cure width for those ones that I mentioned. And then, as we've been talking about during this presentation, the key is really to find the right mix, and having a successful partnership is what's going to make for a successful application. And so compatibility is the key, making sure that between the pretreatment, the ink formulation, and the curing system, there's lots of choices. And so making sure that the choices you make work well together is going to make sure that you have a successful application.
Great. Thank you for that, Mike, and thanks, Huck, and thanks, Wilson. We are going to dive into our audience's questions. If you want to reach out to our presenters directly, please feel free to do so as well. And Mike, the first question is for you. This person would like to know what are the main things they should keep in mind if considering moving to an LED curing process?
All right, thanks, Mark. And I think that's a great question, because this is what we see many, many times. And the key, as I talked about in the presentation, is making sure that the wavelength of the LED matches with the ink that you're using. And often, people will try to switch curing technologies from a very broad spectrum lamp to a very narrow spectrum LED. And ideally they'll be able to use the same ink, but often that's just not going to be possible. And that's why there's specific ink formulations that are designed for LED. So really the most important is making sure that the spectral content of the LED matches the requirements of the ink. If it's not compatible with the ink you're using, then we're going to have to work with the formulator to make sure that you get one that is compatible with LED. And again, that's something we can help with. We have material test centers globally, so we can give you some initial help. But ultimately, as I said, it's got to be a team effort to make sure that the wavelength of the LED is matching the requirements of the ink.
Thanks, Mike. The next question is a good one. Do you typically see a difference in print adhesion on a polyethylene substrate if the polyethylene substrate is hot post-extrusion versus being cold?
Yes. You. Mike, do you want this one?
No, I was hoping you were going to take that one.
Okay, I'll take this one. Yes. A lot of times the hot polyethylene will be, the surface is still a little bit excited. You don't need to have the surface treatment per se, but we still like to see, a lot of people will use flame at the crosshead to take off any remnants of the dye leakage or anything like that. And that's kind of mistaken, as the hot polyethylene has better adhesion. You will get the same adhesion down the line, cold polyethylene, if you pre-treat it with the plasma or with flame, as you would on the hot up by the extruder.
Thanks for that, Huck. Wilson, this one is, would you recommend plasma treatment for nylon 11 or 12?
Sure, we treat those on a relatively regular basis. I don't remember the last time it was on like this where we're printing on cabling, but yes, in other applications we have treated both of those.
This question is, can PTFE need sintering process and pre-plasma?
All right, say that one more time, the first part of that.
Yeah, it says, can PTFE need, maybe it should be, does PTFE need sintering process and pre-plasma? I'm not sure what sintering is.
Yeah, I'm not sure either. The way we do treat it is, again, parallel with the line, so it does have to control. If you're talking about where the wire is, you would have to control where the wire is in the plasma. Um, but yeah, with PTFE, you're going to have to pre-treat it with something. There's a couple of different applications, but there's a lot of people that want to change their current prep method. PTFE is just really hard to print on. So I'm not sure what centering means, but give me a call and we can talk about it.
I can expand on that a little bit too, Wilson. Sintering
Okay.
is the post oven curing, is heating the wire once you have printed it to actually sinter and cure the PTFE into what it's going to become. We have specialty inks that will become part of that jacket if you sinter them into a PTFE or FET jacket. ETFE is going to be similar, but it's not as crucial to do the post centering on the ETFE as it is the PTFE.
Thank you.
All right, we've got a question for Mike. Um, Often lighting in general requires high energy. What is the minimum time required for the ink to cure? And is there any control interface to link the systems to PLCs or I/O devices?
All right, thanks, and great question. I mean, the minimum time is really going to be dependent on a number of factors. So it depends on the ink itself and the irradiance that the UV curing system is providing. But generally on these, I mean, the speeds are continuous. So again, that's one we'd probably have to get a bit more information to give you a specific answer. But I think one of the things we found with working together with Gem and Enercon is we're able to match or even increase speeds on these applications of what customers were being able to do. So the capabilities are there with LED, and absolutely there are ways to interface to PLCs. We have PLC connectors on the units. We also have RS-232, RS-485 connections as well. So many different ways to connect and automate these systems.
Thanks, Mike. We've got a couple more questions. This one, we have a few people asking about what's the best ink for UV resistance?
Okay, for UV resistance, for being out in the sunlight or under a harsh UV environment, the best inks are going to be your heavy pigmented inks. They are going to stand up to the UV better than most anything else. We do have a couple of dye-based inks that hold up very well to weathering and UV exposure, as well as rain and all the other good stuff. But for the most part, you're going to be looking at the heavy pigmented inks and the soft pigmented inks to stand up to the sunlight.
Thanks, Huck. Mike, just a follow-up question to your previous answer. This person wanted to confirm if we were talking in the range of milliseconds or full seconds.
Oh, definitely, we definitely under full seconds is capable. Yeah, milliseconds is definitely possible, but it has to be the right setup for sure.
So what we generally say, Mike, to expand on your answer, our air dry inks are 2 seconds or under for the most part of our air dry inks. We call our UV cure inks immediate or instant. It's well under a second for most every application we have.
That's perfect.
All
Thanks,
right,
Huck.
thanks, Huck. Wilson, we have a question if metals can be treated with plasma.
Yes, very often. So again, copper, aluminum, stainless steel, titanium, just a few of the metals that I know of in our applications currently. So yeah, metals are easily treatable. They start with a higher surface energy to begin with, but you still can treat them and improve on that for especially bonding applications or coating applications, or again, applying the jacket to the conductor.
Thanks, Wilson. And we've got a combination question. This will be our final question today. This person's interested in understanding how to differentiate the requirement of blown ion or flame compared to substrates they work best with. And then secondly, specifically, what would be the ideal setup for silicone and EVA?
we'll start on the plasma side. Yes, there is a difference in flame and plasma when it comes to treating and some of these materials, and you'll get higher energy levels. But generally speaking, even the lowest energy level, let's say if it was plasma, I forget the material that we showed in the slideshow. Usually, the plasma is, even if it's lower than the flame, is plenty before so that you'll get the ink adhesion that you need. So most times, 95 times out of 100, you're using one of the plasma systems for this application. Maybe 1 in 20 or 30 you'll use a flame system.
Great. Thank you for that. I'd like to thank our audience today, and I'd like to thank our panel for sharing these great insights on optimizing wire and cable continuous inkjet printing by managing the surface, the ink formulation, and also the curing process. If you enjoyed today's webinar, please let us know. If you have ideas for future topics, please send us an email on that as well. Everyone who attended the webinar today will receive an email tomorrow with access to the recording and the presentation slides. That will conclude today's webinar. Thank you for joining us, and have a great day.